And we're back. Welcome back from Tuesday. Today we will continue on with our discussion of the control plane. The focus today will be on software-defined networking version of the control plane. And so administratively, we have Project 4, which is the TCP Wireshark experiment that is due on Tuesday, the 14th of April, so this coming Tuesday, the usual 1 second before midnight, 11:59 and 59 seconds. So why don't we begin? So the SDN control plane, software-defined networking was meant to make the switching behavior of routers much more generic and more programmable. And so the network layer historically was done as a set of distributed algorithms. You have routing algorithms, which essentially acts as clients and as servers, and therefore are peers. And in this peer-to-peer approach, routers contain all the switching hardware. They would run proprietary implementations of various protocol standards. And so different router vendors would implement versions of RIP or OSPF, BGP, but they'd add their own, secret sauce to it, so to speak. And you had all sorts of different other so-called middle boxes for different types of network layer functions, things like firewalls that would block traffic, things like load balancers that would distribute certain incoming requests to different cluster machine instances, things like NAT boxes that we learned about will rewrite the IP address and the port number to share one public-facing IP address with multiple private-facing IP addresses. And so right around 2005, there was an increased interest in trying to rethink the network control plane to make things a lot more standardized so you separate out the hardware and the switching from the programmatic directing of flows. And so now you can have a generic box that does this routing behavior, load balancing behavior, NAT-like behavior, and switch-like behavior. So let's take a look at this a little bit more. So let's look at the so-called peer-to-peer router control plane. We had a routing algorithm running in each router instance. So we have our routers, and inside of these routers, we had our local forwarding table. And these local forwarding tables, let me switch on the pen here. We'll try blue. We had our routers, and these routers had local forwarding tables, and these local forwarding tables contained some header information identifying the subnet for destination address, and it had an output port number. And in this local forwarding table, it defined the switching behavior for what path, if you will, or what port a datagram will be forwarded out of and transmitted across the next link. And so this forwarding table controlled the switching behavior, and that was part of our so-called data plane. We also had the routing algorithm, and these routing algorithms interchanged or interacted with other routing algorithm instances. They exchanged information through either link state broadcast or sending advertisements, whether they're BGP or distance vectors and distance vector routing. And so these routing algorithms, when they converged on their individual run of Dijkstra's algorithm or Bellman forward update or BGP forwarding, iBGP or eBGP messages, they download or install in the router a new version of the forwarding table that implements that router's responsibility on the least cost path. And so the collection of forwarding tables that implement the switching decision along with the switching hardware collectively across the network, that's our data plane. And then the set of routing algorithm peers that run your routing algorithms and exchange traffic information or network topology information, that collection across your network is your control plane. And so a logically centralized control plane is what software-defined networking is doing. So here we have all these routing algorithms, and in order to get optimal routes, well, this is effectively a distributed algorithm. They all talk to one another. And now in software-defined networking, we're going to take all of this responsibility about establishing the routes, and we're going to defer that into a centralized location, and that's going to be called the controller. Okay, so let's take a look. So in software-defined networking, we have a distinct, and it's a remote entity, a controller, and this controller interacts with control agents. And so instead of having a routing algorithm running, or routing algorithm process on each router, you have a control agent. And the job of that control agent is to report topology information to the central controller or install so-called flow tables into the data plane. So here we have our control agents, and here we have that remote controller. Now it's centralized, but its implementation could be a cluster or a cloud. So we have this control agent, each one in a router, that communicates topology information in this direction, so that's topology, or in the other direction, it's going to be flow table entries. Oops, forgot the L, flow table entries. Okay, and as we discussed before, flow table talks about a pattern that it matches. It talks about an action that's taken when it matches the pattern, as well as a count for how many datagrams match that pattern. So here we have our remote controller. That calculation of route information is done in one place. And then the result of that is used through the control agents to configure the local flow table that impacts the switching decision at each router. And so the collection of control agents and flow table installations, that's the data plane collection across the network. And now that remote controller, that's your control plane. So all that computation is now in one place instead of scattered around your network as a distributed system. Now, certainly, this has a lot of benefits, and that's what the subject of today will be, is all the benefits for this logically centralized control plane. So what does it afford you? Well, there are a number of benefits. Easier network management. And what does that mean? Well, because it's in one place, you can avoid misconfigurations of routers. And you can also, and this is an important one, have flexibility in your traffic flows. You can do all sorts of things that otherwise in a peer-to-peer routing algorithm approach would require you to rerun Dijkstra's algorithm and completely update your routing table entries. Now, the forwarding decision is now based on a so-called flow table. And this flow table, in essence, allows the control agent and indirectly the controller to effectively program the routers. Now, there's an API called OpenFlow that allows you to tweak and change the bits in the flow table, or will cause changes in the bits of the flow table, and therefore change the pattern that triggers a match, as well as changing the action it's going to take. Now, of course, with this, you can have all sorts of behavior that you can elicit from a single device. So you have a single type of device, you can make it act like a router, like a NAT box, like a link layer switch, all sorts of things. You can even use it to load balance the flows, which in the traditional routing approach would require you to have your routing algorithm update the links and then update them again. You can't have partitioned flows with a traditional routing setup. So you have these centralized programming. It's easier to compute the flow tables and then centrally, and then distribute them where they need to go for each router's role in establishing certain pathways or flows between source and destination endpoints. The other benefit with this centralized computation in the local controller, we contrast that with what happens with a traditional peer-to-peer routing algorithm computation. Now, peer-to-peer, it's a distributed algorithm, and distributed algorithms are a lot more difficult to compute because you have to wait for all of these peer instances to converge. And that's especially apparent when you talked about distance, when we talked about distance vector routing algorithms. It takes time for all of this localized distance vector information to wash across the network, and then eventually all of the distance vector estimates for each router or node stops changing. It allows you to have open implementations of the control plane instead of these closely held secrets that Cisco has a little tweak on distance vector routing. Cisco has a tweak on, perhaps link state routing. You can now open things up. And I like to compare this to, imagine if you bought a Toyota or a Volvo and you could only go to certain gas stations to fill up with Volvo because the nozzle for the gas pump wouldn't fit. By standardizing, you can have a lot more innovation going on. So it opens up implementation of control planes to all sorts of innovations. So in the book, they draw an analogy for the evolution of the control plane to what happened with the evolution from the mainframe computer to the personal computer. Now, this is the System Z10 by IBM. It's a very powerful mainframe computer. It had specialized hardware, has specialized operating system, and very specialized applications. Now, of course, this absolutely served its purpose, but then over time, we had open interfaces, a common x86 architecture, and one of the things that consequently was IBM did is they made the PC architecture spec open. So all sorts of other companies like Dell and Hewlett-Packard and all sorts of Lenovo, all sorts of companies said, okay, well, I'm going to compete, implement to this open interface standard, but how I'm going to innovate to this standard is with certain things that I think make it faster, more efficient, and so forth, more powerful. But as long as I maintain this interface or adhere to this specification to access that computation, any application can run on my system. So that was a huge innovation. So in hardware, you had this open interface, the PC architecture, and then you also had operating systems. These operating systems, some might be friendlier with lots of user interfaces. Some might expose you to the underlying parts of the machine like Linux, but it's very flexible and you can really customize it to suit. Or, something like Mac OS, it's very, very intuitive in its user interface. And this allowed you with these, there are open interfaces. So then now you abstracted the hardware through operating systems, and these operating systems running on these open hardware interfaces, they benefited for different types of users for the operating system. And now these operating systems, especially when you saw the advent of the web, you have these open interfaces so you can have all sorts of applications that you can run regardless of the platform. That's kind of like what your browser did with like Node.js and all these web-based frameworks. Now it doesn't matter for the application. It doesn't matter what platform you're on. And some platforms make different usages of the hardware open interface for certain types of applications. And so software in the old mainframe, they were vertically integrated, or so-called vertically integrated. They're closed or proprietary. It was slower to innovate. Things were really, really fast. Absolutely. That was a benefit. But the industry was very small. It was controlled, that full stack, from hardware going up into operating system to applications. It was controlled by one vendor. Now, in the PC part of this evolution, you have multiple vendors competing at each level. You have lots of competitors at the hardware side. You have lots of competitors at the operating system side, the platform, the runtime, and you have lots of competitors now on these applications. And as long as you adhere to these interfaces, any application can use any platform because Node.js is the same on any platform. Java is the same on any platform. Even Swift, there are runtimes for every platform. Python is the same on every platform. Okay, so these PC world opened up so-called horizontal open interfaces that allows you more innovation across different vendors, why they call it horizontal, and the end result is much more innovation, more people competing, a bigger industry. So that has sort of proven itself out in history. Okay, so let's take a look at one of the difficulties in traditional peer-to-peer based routing. This is traffic engineering. In traffic engineering, the goal is to shape the route your flows take across your network. So what if you have a network operator and you compute your least cost path, and your least cost path would say if you want to get from U to Z, you're going to go along the least cost path, which is along this edge from U to X to Y to Z. Now, absolutely, that's the least cost path. But what if the operator of that network, service provider, wants all traffic that has a source at U and a destination at Z to flow along a different path, U, V, W, Z? Well, there might be reasons why you want that flow. Maybe Z is in a far-flung remote area, and this line is maybe copper wire, and they want to actually use the satellite. So maybe that's satellite, and maybe that's copper. Absolutely, the cost is more to go over satellite, but it's more reasonable with satellite because you don't have to maintain and run as many copper wires long distances because it's not as efficient. You get a lot of signal loss. And so If you want your traffic to flow a different direction, what do you have to do? You have to redefine the link weights so that the routing algorithm computes the routes accordingly. So that means you artificially have to make this link cost less. Maybe that's 0.7, and this less. Maybe that's 0.8, and maybe that link cost is less. Maybe that's 1.8, for example. And in changing the link cost, then when you rerun, whether it's link state routing or distance vector routing, eventually this route from U to V to W to Z will be preferred. Now, of course, these new numbers are sort of a control, if you will, that get the routing algorithms in the peer-to-peer case to react in a way so that a preferred route is given. But these link costs are set artificially to encourage a certain path, but they don't truly represent the link cost. So you have to do a lot of weird tweaks in order to get this distance vector and link state routing, peer-to-peer routing algorithm approaches to work correctly. If you need a new route, whether permanently or temporarily, it's much harder to do because you have to tinker with these edge weights the right way in order to encourage flows to traverse a particular route between a source and destination endpoint. So using link weights as control knobs is wrong. And part of the reason why it's wrong is because not only do you affect the flow between U and Z when you change the weights to 0.7, 0.8, 1.8, for example, you're also going to impact the other flows. The other flows you impact now is other flows that might use that link along the way. And so what ends up happening is not only do you encourage the flow from U to Z to go across that UVWZ, you're also going to redirect other flows that you otherwise might not have intended to redirect. So the using of link weights as control knobs is absolutely the wrong approach. The other thing that's difficult with traffic engineering is, let's say you have a flow from U to Z. Maybe this is Netflix, and you have a browser here, and you want to watch a movie, or a number of people on the network want to watch movies. You might want to redirect some of those flows along this top path from U to V to W to Z, while other of those flows go along U, X, Y, and Z. If you want to split these flows, well, this idea is called load balancing. You don't want to push all the traffic along one route. You want to spread that traffic out to multiple routes in order to balance that load. You can't do that without installing a brand new routing algorithm, because that new routing algorithm now has to somehow establish two pathways that have the same path cost, and now you also need to configure the local forwarding table in the traditional peer-to-peer routing approach. You have to somehow engineer that forwarding table so that some of the time the same destination subset goes out this port, the top port. Other times it goes out the bottom port. So you need to invent an entirely new routing algorithm to make that possible. And you can do it theoretically with subnetting, but how do you decide which of those flows to go from one path and which of those flows to go on the bottom path? You want something a little bit more fine-grained control. Nothing is brute force as using subnetting, because things might change on your network. Things might change in the cluster. You don't have control over Netflix's cluster. So it's really hard to establish which subnets are going to be responsible in your sender-side router. Okay. So you need a new routing algorithm. You need to invent a new one. Another thing with traffic engineering, suppose you want to route differently. Suppose W wants to route blue and red traffic differently. So if red traffic comes into router W, it's going to send it out this port. If blue traffic comes to W, it's going to send it out a different port, right? What if you want to do that? Well, you can't really do it with destination-based forwarding, i.e. link state and distance vector, because if you have a particular subnet entry in a local forwarding table, it's going to make one decision. It can't treat two entirely different flows differently because it's all based on the same subnet. How do you do this? Okay, so let's look at this. In software-defined networking, Again, we have the control plane consists of a remote controller, it's a localized, and it takes on the task of computing your route information. It gets the local topology information from each one of the control agents installed at the router, and this control agent implements the behavior arrived upon when the routing algorithm in the controller makes its decisions. And so all sorts of applications you can implement in this local controller. You can implement traditional routing. That is the determination of what port the datagram goes out of at each router, and that's controlled by the flow table. And these are the flow tables. And these flow tables control the switching decision collectively in the data plane across all of the routers in the network, in the autonomous system. So you can do the routing. You can also do access control. Which flows are allowed access to certain parts of the network. And it's really, really powerful to do that at the network level, because now you won't even allow certain types of traffic to go in certain parts of your network. You can also do something like load balancing, right? The determination of sometimes a flow, part of the flow goes across one path, and other times the flow goes across another path, even though they might have the same destination address. It's a lot easier to do with this centralized idea of the control plane decision making and computation. So you have a generalized flow table. It's based on the standard OpenFlow, and it's flow-based forwarding, and it implements certain behaviors that are triggered based on matching patterns in different layers of our packet information. And then you have the control plane. It's separated from the data plane. So the switching decision and the decision making is separated out. So now you can change the decision making without having to disturb the switching implementation. So if the switching implementation is not disturbed, you can make these things commodity, you can make them generic, and they can perform multiple functions that you can control through hardware, and you can also make them very fast. Okay. So the control plane functions are external to the data plane, and as such, you could specialize on control plane functions and know, just like that gas station, gas pump example that I gave earlier, and know that your special routing or your special control global decision-making function will work on any device as long as they support that control plane interface, namely OpenFlow. Okay, so you have programmable control applications. You can get different behaviors from the same physical device just by making a software application change, depending on the API that runs. And the interesting part about this is that each one of these is accessible as a web service API call. So here's some program. The program can initiate a service-oriented architecture type call into these applications and get one of a number of features or behaviors out of the routing infrastructure that benefit this particular program's flows between a source and destination endpoint. Okay, so let's take a look at the data plane switches. Because we commoditize them by making them adhere to a standard interface, we can make them fast, we can make them simple, and we commoditize them. And therefore, we can get a lot more competitors that will specialize maybe on inexpensive switches, maybe on very fast switches, maybe switches that can be put in small form factor embedded, and so forth. And so the switches implement the generalized data plane forwarding. So they implement the configuration using these flow tables. And so the switch flow table is computed, and it's installed or configured by the control agent. And there's a control agent in every single switching device. The API for the table-based switch control is called OpenFlow, and it defines what is controllable and what is not. Controllable means what pattern you're going to match in the datagram or in the packet, and what actions are taken in response to a pattern match. And it also includes a protocol for communicating with the controller, and that's also handled by the OpenFlow standard. So not only can you change the behavior of the switch in the data plane, you can also communicate with the controller, and that communication is either to send topological information or to receive directives to change the flow table. Okay, so now you have the SDN controller, and this is kind of like a network operating system. It is an operating system of sorts, a runtime, and you can call functions on it, and these functions allow you to reconfigure the flow behavior given rise by all of the switches in the data plane. And so it maintains network state information. It collects all of that from the control agents from the data plane. It interacts with network control applications above, so it offers services that allows each of these applications to do things on the network. Right? So the SDN controller is the one that carries things out. It effectively, like a traditional desktop or machine computer operating system, it shares the resources of the underlying hardware. The SDN controller, as a network OS, it shares the resources among all the applications. It shares the resources of your switching infrastructure, your switching hardware, and therefore the flow behavior. And so from above, the SDN controller interacts the northbound API, as they call it, with all the applications, the control plane applications. And then from below, the southbound API, it interacts with all of the switching devices in the data plane. And it's implemented as a distributed system for performance, this controller. But it doesn't have to be. It can be a single machine, but of course, you want to make it a cluster or cloud or distributed system to get some scalability and some fault tolerance. But it's still centralized in the sense that it is doing the work of this global type of consideration for evaluating flows and paths instead of deferring that to each of the individual router devices. Okay. So then up top, we have the network control applications. And this is where all the thinking work happens. And in fact, not only could you do a traditional routing application, you could also start to use things like machine learning that will adapt your flows depending on the prevailing instrumentation or sensors, if you will. And those sensors are just traffic information that gets streamed in by the control agents from each of the control agents at the network layer, or rather at the data plane layer. And so now you can do all sorts of interesting things, not just a fixed routing, but imagine an adaptive routing that tries as much as possible to do interesting things with load balancing flows across multiple paths between source and destination. So the network control apps implement control functions, and they use the lower level services, the APIs provided by the SDN controller, and it's unbundled, meaning that these apps can be provided by multiple third-party providers. And this is distinct from the routing vendor. So Cisco won't control all the applications. You yourself could say, aha, well, I want to compete with an interesting routing application or routing approach. I'm going to do that, and you don't have to be beholden, if you will, to the device manufacturers. And so you can provide these applications from any third party, and it's distinct from the routing vendor, and it's also distinct from the SDN controller. Okay. And we saw this happen with these sort of app store-like models on these smartphones. You have many, many, many more people, individuals even, that are joining the fray and innovating with all sorts of interesting applications. So now the network is an application, right? The network layer is programmable. And because it's programmable, now you can have lots more innovation and lots more competition, which is always a good thing. Okay, so these are the components of the SDN control layer. Again, you have the application layer above for the SDN application layer, and then you have the data plane below. All sorts of interfaces and abstractions for network control applications. Things like computing network graphs. You need that as a data structure in order to do routing. You have the support of representation state transfer, or RESTful APIs, the ability to make remote calls back and forth. It piggybacks on HTTP. You have things like intent. What is it you're trying to accomplish? Load balance, least cost, stuff like that. You also have network-wide distributed types of applications and robust state management, things like collecting statistics, APIs for collecting statistics about the number of packets, so the amount of data and the amount of congestion and things like that, things you might collect from multiple routers or multiple devices on the network. You also have link state information, host information, and switch information. And then you also have the communication layer part of the SDN controller, things like OpenFlow. That's the implementation of these OpenFlow constructs in the API, and things like device management, SNMP, Simple Network Management Protocol. You can collect operational statistics and information on your individual devices, and also push out things like patches or temperature and measuring the temperature and things like that, right? So this low level is the communication layer to and from each one of the devices in the data layer. And then here we talk about distributed types of API function calls, and then you have interface pieces that applications would use from above. And this is your SDN controller. So the communication layer allows you to communicate between the SDN controller and the switches. It's all that low-level stuff. You can think about it from an operating system's perspective. It's how you interact with the low-level devices. These are kind of like your device drivers that access and control the low-level features and behaviors of the hardware itself, these switch boxes. And then you have network-wide state information. This is kind of like your OS runtime. This acts like a kind of distributed database that collects aggregate information from these different places on the network. Now, certainly to collect statistics on the network, you have to interact with the communication to get data to and from these individual devices. And then you have the interface layer that allows network applications. These are the APIs, like the system calls in an operating system. They provide the abstraction that allow applications to access the different features to do things in the application. Right? So your applications might say, allocate memory to your operating system, open up a file to your operating system. The operating system interacts with the disk. That's what this lower layer does. So that's like your device drivers. And this is your OS, your runtime services. And this is the system call interface, right? And this allows applications to make use of the services of the SDN controller. Now, if anyone's interested, this would make a fantastic capstone project to look at SDN networking and to try to write an application, or rather write an application that implements some interesting type of behavior. Okay, and so the OpenFlow protocol kind of stitches all of this together. It operates between the controller in the middle and the switch, and it uses TCP to exchange messages. It's a good idea to encrypt these messages, but encryption is optional. There are three classes of OpenFlow messages. There's controller to switch type messages. There's asynchronous messages, switch to controller. And the reason why these are asynchronous is because these switch to controller messages are triggered when there's some condition in the controller. Now, if you think about it, when you get a match action, you send information. When you have something occur, you send information. If you're doing network management, you query and it sends back its health status and error reporting information. And so this asynchronous is switched to controller, and then you have symmetric types of messages where it's not asynchronous, it's both the same, and these messages are used for miscellaneous types of things like management and error reporting and stuff like that. So OpenFlow controller to switch messages. Some of these features, the controller can query what the switch supports. So the controller says, hey, do you support this type of capability? And it says yes or says no. There's configuration types of messages. Controller queries and sets which configuration parameters are going to be enforced on each one of the switches. There's a modification of state message to add, delete, or modify entries in the flow table. Right? So you might change the pattern that matches, you might change the action. And there's also packet out types of messages. The controller can send this packet out of a specific switch port, right? So that's a specific type of message that says, switch, send this message out of port. Okay. And then these are switch to controller messages. So that's in the reverse direction, from the switch back up to the controller. Transfer packet to the controller. Right, so that's the reporting. Maybe your controller wants to collect statistics about packets flowing across. Flow removed. A flow table entry gets deleted at the switch. The switch informs the OpenFlow controller that, hey, I'm striking this entry out. That means my behavior that you're expecting is going to change. It has to report that, as well as the port status. Inform the controller of a change on a port. Maybe someone has installed a new port, or maybe a port is dead. Something's wrong with the hardware. Unfortunately, network operators don't program switches by creating and sending OpenFlow messages. Instead, you use a higher level of abstraction at the controller. You're using some other API call. You never just sending these directly to the hardware in the same way that you would never do something directly with a disk controller. You let the operating system do that. You just set that configuration information in your operating system kernel parameters, and the operating system takes the right action based on that. So the control data plane interaction, here's an example. We start out, and the first message in router S1, let's say it's experiencing a link failure, and it's using the OpenFlow port status to notify the controller. And so links are just ports, and links are pieces of hardware, and maybe something's wrong with the link and it's starting to fail, right? Maybe there's copper wire is starting to degrade, there's a break in the copper wire, and it keeps disconnecting and reconnecting. Nonetheless, link failure is reported from router S1 in this example through the port status message, and it notifies the controller. So through OpenFlow, the communication between the hardware and the controller, we get that first message here, and through OpenFlow, it sends that message in. Okay, so now the second message, the SDN controller gets the OpenFlow message, and it updates its global statistics, i.e. The link state information for that particular device. Now that goes up into the network graph because the edge weight or something has changed. The edge weight has changed for this link, and so that network graph has to change the decoration that it had associated with the mathematical representation of that edge. And so now then that message gets sent up into the application for Dijkstra link state routing algorithm. It recalculates the routes based on that network graph that is being maintained, the global information collected from multiple places. That's a mathematical abstraction, as we said before. It then computes the least cost path, and then it interacts with the SDN controller, send message 5 down, and it computes new flow tables. Okay. When it sends that down, it updates the graph here through this edge as it goes through the API part of the SDN controller. It then computes the new entries for the flow tables maintained for each of the devices that are involved. And the controller then uses OpenFlow, message 6, to push down the new directives into the flow tables, and the control agents at each one updates the tables, effectively reconfiguring the flows to represent that needed change. So next we will talk about ICMP, and we're all going to talk about briefly one topic, namely traceroute. ICMP stands for Internet Control Message Protocol. Internet Control Message Protocol is another feature in the network layer, and it's used by hosts and routers to communicate information about the status of the network devices. Things like error reporting, if a host is unreachable, what protocols are available, and things like the echo request reply. This is used by ping. ICMP, Internet Control Message Protocol, you can think of it as sitting above IP, right? It is carried directly in the IP datagram. So it resides or exists in the network layer, but you can think of it as being on top of the network layer. So these are the different types of ICMP messages. And the one in particular that we're going to use is the TTL field, TTL expired. So here there's a tool called traceroute, and traceroute makes use of ICMP. And what traceroute does, it sends a series of UDP messages over the network, and it first sets a time to live field to 1 in the network layer. And as this datagram gets to a router, before the router forwards that datagram, it decrements the TTL field by 1. When that TTL field gets to 0, it sends back an error report through ICMP that the timeout has, the number of hops has been exhausted. And you can use this in traceroute to effectively measure or report on all the routers between a source and destination endpoint. How do you do that? Well, you initiate an ICMP message sending 3 probes, and then you measure the round trip time that it takes for that request to come back from the router. So if its TTL is initially set to 1, it hits the first router, decrements to 0, and it comes back, and you know how long it took for the round trip time for that message, to get that response back, and you know how long it took to get to the first router. Then you resend it with a TTL of 3. So once it reaches the second router on the path between the source and destination, it gets sent back. And all the while, you set a timer before you send it, and then you stop the timer when you get back the ICMP error message. And then you stop your stopwatch and you know how long it took for the round trip time to get to from that router. You do it again and again and again, 3 probes, until you finally reach the destination. And so the datagram has reached its destination for some TTL field value. And when the ICMP message arrives, the source records the round trip time. So the stopping criteria is that the UDP segment eventually will arrive at the host that it's destined for. And the destination returns the ICMP port unreachable message, type 3, code 3, and then the source stops sending with this increasingly incremented TTL field that knows it's reached the destination. So all the while, for each one of these probes, it records the round trip time, and now you have a measurement for all of the hops, all of the stops, all the routers along the way between the source and the destination. So let's take a look at this. I'm going to exit. So let's take a look at this. Here I'm on my terminal, and let me type which trace route. Okay, trace route is installed. So let me say trace route. How about Netflix.com, right? And so it'll do a DNS lookup, and it'll get the IP address for Netflix.com, and then it will do the trace route, sending each one of these ICMP messages. Now you'll see 3 numbers here. Those 3 numbers represent the first probe, round trip time, second probe, round trip time, third probe, round trip time. Now, not every router is going to respond to the ICMP echo request with a time to live field, because some vendors feel that if you can identify a router, you can attack it. Now, I'm on Verizon network, and so here, the first hop, that's my default gateway. Second hop, that's the first router on the other side of the internet to get me to Verizon's network. And then here, this is Philadelphia. We take 2 hops. Well, there's first message, second, third. Okay. And you'll notice here, it takes an increasingly large number of seconds for the round trip time. So first router, it's very small, 2 and some change. Second hop, third hop, it's 12 milliseconds. Next one, it's 10 milliseconds. That's weird. Then we have 9 point something milliseconds, 14, 15, 16. And so eventually it will find Netflix, but you'll notice there are quite a few hops along the way where it does not tell you anything. Those network administrators have chosen to have their routers not respond to these ICMP. So I encourage you to tinker around with traceroute and see for yourself what routes your communication takes to destination. So with that, I will end there, and this finishes our material on the control plane and finishes our material for Chapter 5. So I will see you all online on Tuesday. We've certainly learned a lot. I will see you then.